Hey guys, welcome to AI Tech Talks with Carl. Today we are going to be going over the correct implementation for decision tree regression from scratch. I will go over each line of code and show you how the algorithm achieves a time complexity of n times log of n. Let's go ahead and get started. The reason I say the correct implementation is that this version has a running time of big O of v times n log of n, where v is the number of features and n is the number of samples in the dataset. This running time is derived from the CART, or Classification and Regression Trees algorithm, and is dominated by finding the best split for a node of the tree. Let's begin with the Python code. The first thing to do is import all the libraries, including the NumPy and GraphViz library, because I'm going to show you how to make a cool image of the regression tree used to fit the model. The first line here is to retrieve the diabetes dataset from the following URL website and save it to a text file named diabetes.txt. This famous regression dataset has 10 baseline variables, including age, sex, body mass index, and blood serum measurements to predict the target variable of response of interest. According to the website, the response of interest is a quantitative measure of the disease progression 1 year after baseline. The dataset is then loaded into a NumPy array with np.loadtxt, with the first 10 columns as the features and the 11th column as the target values of the observations. The features are then standardized by subtracting the mean of each feature and dividing by the standard deviation. We can then use NumPy advanced indexing to split the training and test sets up into xtrain, xtest, ytrain, and ytest. If we have a regression tree like the one here, we have to define a class that will contain a node in the binary search tree. This class is usually called a self-referential data structure because it will refer to the left and right children of the tree, which are also nodes. So if we instantiate a root node, that node will refer to the left and right children nodes of that parent node. Let's go ahead and define the node class, which is the self-referential data structure. The class has 3 instance variables of info, left, and right. The left and right variables will hold the left and right children nodes of the parent node of the tree. The info variable is just going to be a dictionary holding the information of each node. And for example, if it's a decision node, we need to store certain values like a threshold and the particular feature that is used to split the data in the tree. So otherwise, the node is a leaf node, and for those, we just need to store the value to output when an observation hits that leaf. So now we define the DecisionTreeRegressor class and pass the min samples split and min samples leaf and max depth into the constructor. Each of these are explained in the docstring of the class above. So the min sample split is the minimum number of samples needed to split a decision node, while the min samples leaf is just the minimum number of samples allowed on the leaf. And the function to build the binary search tree is the build tree function. We define a best split dictionary to hold the information for the best split. If the number of samples in the feature matrix is greater than the min sample split and current depth is less than the max depth instance variable, then we can look for the best split to be able to split the actual node. So we call the get best split function, which returns a dictionary with the feature index, threshold, and RSS for residual sum of squares keys set. The feature matrix X and target value array Y is split into the X left, Y left, X right, and Y right constituents. The build tree function is then recursively called to instantiate each of the left and right subtrees of the parent node. If the if statement returns false by not having enough samples, then the value key is set in the best split dictionary, and the Y target array is calculated for the leaf node. Now, I know recursive functions can be tricky, and it still trips me up sometimes, but I like to think about it hitting the last node in the function. So left subtree equals self.build tree of X left, Y left, and then current depth left plus 1 is going to be called, and after it doesn't hit the if statement, it's going to return a node object. Then it's going to return the last decision node and bubble all the way up to the root node, where it eventually returns the root node to the caller of the build tree function. Now we have to find the best split for the regression tree with the getBestSplit function. We define a best split dictionary and define the RSS key as infinity. Here we have to loop through over each feature and possible threshold that is in the dataset. Now, many implementations use NumPy to calculate the variance or sum of squares of the current node that we are trying to split, and this is actually not the correct way to do it. It leads to a very slow running time of big O of v times n squared due to the getBestSplit method. Let's take a look at that more closely. Say we have a for loop that loops over the number of features and the number of thresholds like this. We make a call to np.var to compute the variance for the left and right data of the split. What would be the running time of this? Well, the call to NumPy takes big O of n, and the loop over the number of samples also takes big O of n. Therefore, the running time is actually big O of v times n squared due to the call to np.var in the for loop. This wouldn't be correct, so we have to use a different formula for variance and just update the sum inside the loop. This way of calculating the variance allows for a running time of big O of v times n log of n, with the sorting step dominating the runtime. So now before we loop through the number of samples in the dataset, we have to sort the features and labels by calling np.argsort on all the examples for the feature index. Then, since we are starting from the leftmost side of the sorted array, there will only be one observation on the left side. We initialize the left sum and sum squared to 0 and the right sum and sum squared to the whole data set, since all observations will fall on the right. Again, the number of observations for the left side is 0 and the right side is the full length of the data set. We loop through the number of observations in the parent node and update the left sum squared, right sum squared, and right sum variables. All we have to do for this is just add or subtract the squared value of the sorted value and unsquared value respectively to update these terms. The count for the number of samples in left and right children is then updated. Finally, we implement the residual sum of squares formula if the number of samples in the leaves are both greater than min samples leaf. Then, if the current RSS value is less than the RSS value in the BestSplit dictionary, we update the corresponding information for RSS, feature index, and threshold. The BestSplit dictionary is then returned. Next, the fit method will be the actual function that trains the model. There is only one line in the method, and it is to build the tree with the build tree method that was defined earlier. We pass the X and Y dataset into the method, and the root node of the tree is returned, and each of the left and right variables in the node refers to the left and right children. After this, we can make predictions of all observations in the test set with the predict function. List comprehension is used to generate a list of all predictions where each prediction is computed from the make prediction function. In the recursive make prediction function, we pass in the parent node of the tree, so this is either the root of the tree or the node that we are trying to make a decision from. The features of the observations is also passed in the X argument. The first if statement asks if the correct node has a value key in it, meaning that the node would be a leaf node and the mean value would be returned. If not, though, the node is a decision node, then get the value of the particular feature in that decision node and compare it to the threshold for that node. If the feature val is less than the threshold, then recursively call the make prediction function on the left node, else recursively call it on the right node with the tree.right. This will return the mean values that are stored by the build tree method in the correct leaf node by traversing through the tree. Then we just have the save tree method to print the tree, which I'll be explaining in a little bit. Now we can instantiate a DecisionTreeRegressor object and pass the max depth of the tree equal as 3, which will give us 4 layers of the tree since the index starts at 0. The tree is then built with the fit method and the self.root instance variable is set to the root node of the regression tree. We can then use the predict method to predict the target values in the test set and calculate the mean squared error by subtracting the target label array from the predicted values and averaging the squares. We can also call the save tree method that we defined to print the tree in a nice graphical representation. This uses the GraphViz Python module, and this is the same module that scikit-learn uses, and I have the method defined in the DecisionTreeRegressor class. Let's go ahead and run this, and as you can see, it's very fast with that big O of vnlogn running time. We get a mean squared error value of 3,771 with a binary tree here. This shows each feature that was used for prediction with the feature index and threshold in the decision nodes. Then the leaf nodes display the prediction for the disease progression target variable.
So that's it for this Tech Talk, guys. If you liked the video, please support the channel by subscribing and sharing with your friends.